Right, so we're going to finish up 4.2. So we looked yesterday at sketching rational graphs. And for yesterday, we looked at graphs where the degree of the numerator was less than or equal to the degree of the denominator. So we might have looked at problems like this. 8x squared plus 2x plus 1 over 3x squared minus 5. That's a case where the degrees are equal, and you end up with a horizontal asymptote at 8/3. We also looked at the case where the degree of the numerator was smaller. So 8x plus 3 over 2x squared plus 5. When you find the EBM of that problem, you're going to end up with an x in the bottom of a fraction. Okay, the EBM of this would be 4 over x. Because you end up with an x in the bottom, it goes to 0. So when the degree in the bottom is bigger, you get a horizontal at 0. When they're equal, you get a horizontal asymptote at those numbers, whatever they are when you divide them. But now we're going to look at what happens when the degree of the numerator is bigger. And it turns out that it's not, the difficulty here doesn't just have to do with it being bigger, but it has to do with relative to the denominator, how much bigger it is. So if you had 8x squared plus 3 over x minus 4, that's not too bad, because the degree in the top is bigger, but it's only 1 bigger than the bottom. If you had something like 5x cubed plus 6 over x squared minus 7, it's kind of the same difficulty because the degree here is only 1 bigger. When it starts to become more complicated is when these degrees get further and further apart. So like if the degree in the top was a 4, and the one in the bottom is a 1, now they're 3 apart. That's going to be a little bit more complicated picture to do. So ideally, these are always going to be either 1 or 2 apart from each other in the ones we do. When the degree in the top is bigger, there's this other thing that we can find, and it's called an end behavior asymptote. The EBA, which is what I'm going to call it, takes the place of a horizontal. When the degree in the top is bigger, there are no horizontal asymptotes. So no horizontal asymptotes when the degree in the top is bigger. This takes the place of it. So let's say we had 2 polynomials. So we're going to do a problem in a minute. We're actually going to do this one. And the degree in the top is bigger. I'm going to want to find the EBA. Basically, what's taking the place of the horizontal asymptote in this problem. So remember, when you divide h of x by g of x using either long or synthetic division, you will get a quotient and you will get a remainder. Say it like this. Q of x is the EBA. So it's nothing new. It's doing something we've done before, which is division. We're just calling the quotient something different. The quotient is the EBA. So do your division, long or synthetic, and write down the quotient if you're asked for the EBA.
Even if there's a remainder?
The remainder doesn't matter.
Okay.
That's what EBA stands for. Just one more reminder about that. And the remainder ends up being insignificant when x gets larger and larger and larger. And it wasn't really that explain that, but if you look at the remainder, that's the EBA. The remainder part, well, think about g of x. G of x is what you divide by. As x gets bigger and bigger and bigger in this bottom polynomial, what you're going to end up doing is dividing by something that's getting bigger and bigger and bigger. So the remainder basically turns into 0. It's never really 0, but it gets smaller and smaller and smaller. So that's why this part doesn't matter. I wasn't really going to explain, but all you need to know is q of x is the EBA and behavior asymptote. So let's take this. Let's find the quotient, the remainder, and the EBA. Can I use synthetic division on this one?
Yes.
Yep. What would go on the outside? 2. And the inside?
2, negative 4, 0.
Good. So let's divide it. For synthetic division?
Yeah.
So the number after the minus sign goes on the outside, and then all my coefficients, including any that I'm missing.
Oh, that's good.
All right, so let's divide it. Bring down the 2. 2 times 2 plus negative 4. 0 times 2. Add it up. 0 plus 0. 2 times 0. And 3 plus 0. We don't really care about that. So we did the division. Quotient, remainder. Oh, we do care about the remainder because they asked for it specifically. Other than that, asking for the remainder specifically, the remainder isn't useful. All right, let's start with my quotient. What is my quotient? Yeah?
It's just 2x squared.
2x squared. What about my remainder?
It's
3. And what about my n behavior asymptote?
3. Oh, sorry. I thought those were 2x squared.
2x squared.
Are they going to ask us for both of them? Or the exact same thing?
No, not really. I'm just emphasizing and making sure people know they're the same. So, notice what we just wrote there. We have an asymptote, and here's the formula for it. So, usually, when we write an asymptote, at least the ones we've done so far, they've been horizontal or vertical. So you might have something like this. And your graph is getting closer and closer to the asymptote, and the asymptote was always a straight line. Well, what can happen now is the asymptote can curve. So the last asymptote was it 2x squared?
Yes.
So if you sketch the parabola 2x squared, it might look something like this. That is your asymptote. And your graph might do something like this. Your graph will get closer and closer and closer to that asymptote. And there might be another piece on this side too. But the idea is now you have a curve that you're getting closer and closer to, rather than just a straight line you're getting closer to. The bigger the difference between the degree in the top and the bottom, the more complicated the graph gets. This was a difference of 2, so you get a parabola. If you had a difference of 3, you would have a cubic polynomial as your asymptote. We're going to be focusing on degree 2 or less. Okay, that's what we're going to focus on. So remember, there's a difference between the EBA and the EBM. Okay, the EBA is what we're learning about right now. It takes a little bit more work to find an EBA. You have to do long division or synthetic division. EBM is super easy. All you do is take the highest degree term in the top, divide by the highest degree term in the bottom. Depending on the question, sometimes the EBM and the EBA come out the same. We don't really talk about EBA with the kind of problems we did yesterday. But for the ones we're doing today, we could talk about both of these, the EBM and the EBA. It might be the same and it might be different. And the third point that's important is for the kind of problems that we did yesterday. That was where the degree of the numerator was always smaller or equal. We had straight line asymptotes. We had verticals. We had horizontals at 0. And sometimes we had horizontals at a number that wasn't 0. Well, now, when we look at the kind of problems we're doing today, asymptotes can start to curve. Not just the graph is curving, but the thing that we're getting, the dotted line that we're getting closer to, is curving. So we're going to start by looking at that problem we were just working with, because we already did the work and we found the horizontal asymptote, and behavior asymptote. And I'm going to show you that it is actually an asymptote. So we're going to take the problem we just had. So I'm going to go back to it. I'm going to type it in. And I'm going to graph the EDA. And let's see how it looks. So I'm going to type in 2x cubed. So actually put it in parentheses. 2x cubed minus 4x squared plus 3. And divide by x minus 2. Now, what value is not in the domain here? 2. I'm going to assume that the numerator doesn't factor with x minus 2. I could be wrong, but most likely that's going to be a vertical asymptote. So we're going to have a vertical, and we have an end behavior asymptote that's a parabola. 2x squared. What I'm going to do for that one is I'm going to make it dotted. And I'm going to make it thin, okay, because that's how we usually like to make an asymptote, pretty thin. And let's do zoom 6. So in blue is the original. I'm probably going to have to set my Ymax. Oh, I didn't type that in right.
Yeah, you multiplied it to 5.
Yeah, I can tell right away I didn't do it. So let's put in divided by. I'm going to set my Ymax higher.
How do you make the space like that?
To insert, second, and then you can press the delete key, insert, and then it'll put something in place rather than type over. Okay, so I set my Ymax, I think, at 25. So let's see. So we get something that kind of wants to be a parabola, but
I see.
it can't. So those red dots are an asymptote. Maybe I should have made it solid. But what's happening is we've got a vertical at 2. So that's part of it. And the other part is this parabolic asymptote. So this piece in blue that's up here and that dotted parabola, they're getting closer and closer as you go up to the right. And they're getting closer and closer and closer together as you go up to the left. So those are my 2 asymptotes in this one. Any question on that? Generally, you wouldn't have like 2 vertical asymptotes and a parabolic asymptote, because now it's getting kind of complicated. So 2 asymptotes in a problem like this would be it. You would not have 2 verticals. Just 1 vertical and 1 curve. So we did that. That was purely just a calculator question. And now let's try to graph that one we just did by hand. So the first step to graphing something like this would be find your asymptotes. We found the EBA by doing long synthetic division. And what was the EBA again?
2x squared.
So y equals 2x squared. I'm going to graph that as a dotted line in a second. Vertical asymptote was what?
I don't think we solved it. Or like, oh yeah.
X equals 2.
On graphs, right?
That's really all you need. If you draw those two asymptotes and then plot some points, I think you'll be good enough. Yes?
How do we get the EBA from synthetic division?
So you look at your answer, and then the last number on the right is the remainder, so you can ignore that. And then the numbers right here are the quotient. The one on the right is the constant, the coefficient of the linear term, and the coefficient of the squared term. There is no linear term, and there is no constant term for this one. Okay, so let's sketch the parabola 2x squared. If you plug in 0 for x, what do you get for y? 0. So we've got the point 0, 0. What if you plug in 1 for x? What do you get for y? 2. What if you plug in negative 1? 2. It's going to be symmetrical. Negative 1, 2. Remember, on my y-axis is going by 2s, my x-axis is going by 1s, and we saw that because I needed my y-max higher to see this graph. What if you plug in 2 for x? 8. So 2, 8. You're also going to get negative 2, 8. Can we fit 3? Yeah. What if you plug in 3 for x? 18. So 3, 18, negative 3, negative 18. I'm just plotting my asymptote, but it's a parabola, so I need to figure out a few points to make a good sketch. So now, just the best you can, try to make a parabola out of that. It's pretty good. Put your vertical in at x equals 2. And what usually ends up happening is these kind of graphs are in 2 pieces. One of them usually ends up kind of tucked in that section right there. And the other one usually ends up somewhere in that space. So those are usually the 2 pieces. To figure out what's going on, we're just going to plot some points. So let's do second table.
Turn it on.
Yeah, we got to turn it on. First thing you want to do is pick a point somewhere to the left and right of the asymptote. So what's a value a little smaller than 2? 1.99. And I can see that I'm up at I'm down negative 300. So just before 2, I'm way down there. A value just after 2? 2.0, let's go even 0, 0, 1. We're at 3,000. So just after 2, we are way up there. Okay, I'll do these in black.
Sorry, what's the
So black are going to be actual points on my graph. Okay, what would be another good value to pick to start being able to draw this picture? What? Okay, we could do negative 10. I think it's going to go way off the graph, so we went too far. So we can't do that one. Yep.
Or like negative 5?
We can try. Negative 5, we're up at 50. So still off the graph. Yep. 2.5. Yeah, 2.5 would be a good one if you want to check out what's happening in that other section. At 2.5, we're at 18.5. What's y2? Oh, that was my EBA. Okay. So 2.5, we're at 18.5. So 2.5, maybe right about there. I would even do, you could try 3, but I think 3 is going to be off the graph. 3 is up at 21. So yeah, we can kind of estimate that. 3, 21. So I can kind of see what's happening here. We have to stay pinned in between those asymptotes.
Oh, wow.
And that's the section we get up there.
Wait, sorry. Okay, what did you plug the numbers into get the points?
The table.
Oh, okay.
Second table. Now, how about what's happening in the other section? What would be a good value? Yeah? Yeah, I think -3 might fit. Yeah, -3, 17.4. So there's 18, so just below it. All right, so I can kind of see what's happening here. Staying very close to the asymptote for a while. What would be a few other good points? -2, yeah, we could definitely do that. We're at 7.25. So 6, 8, 7. So still staying pretty close. All right. -1. We're at 1. So -1, 1. Another one? 0 would be good. 0, -1.5. Probably about right there if I go by 2s. What would be another good one? Yeah, I would say 1, -1. So 1, -1, maybe about right there. And then we know from there we're dropping down. So to me, what looks like is happening is this. It's curving down. And I think there's actually going to be a local maximum right there. It looks like it curves back up a little bit. And then comes back down. So it's like it wants to be a parabola that connects, but it can't because of that vertical asymptote. That vertical asymptote basically takes the parabola, cuts it, and breaks off that piece and pulls it down and bends the other piece up. And if we hit graph, that's pretty much what we got. And that's the most complicated type that we look at today.
Are we going to do another one of those?
Not a parabola right now, but I am going to do another one. Yeah. So the key with the parabola is you graph both your asymptotes and then plot as many points as you need to. Okay, we did it in, we'll do 7 points maybe. We didn't use all those. Yeah, 7, 8 points, something like that. So just plot as many points as you need to get a good picture. And keep this in mind. It's usually in 2 pieces.
Okay, this actually seems a bit simpler than the ones yesterday.
Yeah, there's less asymptotes.
Yeah. It's like we need to find less in order to be able to have a complete graph.
Yeah. Now this one's going to be a little easier than the last one because what's the degree in the top? 3. What's the degree in the bottom? How far apart are they? 1. So this EBA is going to be a degree 1. When you graph something that's degree 1, what does it look like? Linear.
Just a line.
But what kind of line?
Is it vertical?
No.
No, that's not what I'm talking about.
Yeah?
Is it a horizontal?
No. No horizontals today. No horizontals. So what other option do we have?
Linear?
Yes, it is going to be linear, but can you be, and it's not horizontal. It's going to have a slope to it. So this is going to be a graph that has a y equals mx plus b asymptote. So it's still linear, but it's going to be slanted. It's going to have a slope. So let's find it. So can't use synthetic division. That's okay.
Why not?
The bottom is not of the form x minus a number.
I see.
Did I get everything? X squared plus 2x minus 3, 2x cubed, 7x squared, 0x squared. Okay. What do you get when you divide x squared into 2x cubed? X. Is that what someone said? 2x. Okay. So 2x. Multiply it back out. What's 2x times x squared? 2x times 2x. And 2x times negative 3. Okay. And what do we do with these columns? Subtract 7x squared minus 4x squared. And 0 minus 6. 6x. Bring down your next term. What's x squared, or 3x squared, divided by x squared? 3. And basically, you're done. That's your quotient.
Oh, okay.
If you want to keep going, you'd be getting the remainder, but do we need the remainder? No. So that is my EDA. Okay, let's graph 2x plus 3. So up to right. Go the other way if you want. That should be enough. Okay, I'm going to zoom out so it's just easier for me to draw it. Okay, so we've got our asymptote that's on a slope, and that's also called a slant asymptote, which I think I'm going to tell you in a second. What other kind of asymptote do you think we should check for? A vertical. So let's see if this is where you factor the denominator and see what the zeros are. Okay, does that factor?
I don't think so. Well,
Plus 3 minus 1. X squared plus 3x minus 1x. Perfect. So verticals are at what two numbers?
Is there some strategy to factoring besides just doing it in your head?
There are different strategies, yes.
I was thinking of what it could be.
Yeah, there's some little kind of fancy tricks you can do that some people have learned. But yeah, there are some tricks besides just guessing. So what are my two verticals? 1 and negative 3. All right, so we got 2 of them, but at least we don't have a curved asymptote. So there are 3, but there's no curve. So x equals 1, and x equals negative 3. So the asymptotes are my guides. I'm going to end up with a sketch in 3 different pieces. I kind of know where they're going to be already. But if I didn't, now I'm just going to use the calculator and plot as many points as I need to. Always check points near the asymptotes. That's the first thing you should check. All right, let's clear that. And put the original. You can put the factored problem in, but the original's probably better. Because we know it's right. So 2x cubed plus 7x squared minus 4 divided by x squared plus 2x minus 3. Okay, what would be a good value to check in my table? All right, so let's check near the asymptotes first, and then I agree negative 4 would probably be another good one after that. But let's get the asymptotes done first. Yep.
0.99.
0.99. Okay. So we're at negative 1200.
Okay, I think the decimal like of a fraction. Is there some way to change that?
In your table?
Yeah.
It's probably under mode, and there's probably something like math type.
Okay.
My calculator doesn't have that option. Looks like you got the one that's a little newer. But it's definitely in mode. I can help you find it if I can see the screen.
Oh no, okay, sorry. I just put in something different.
Okay, another good value.
1.001.
1.001. Okay, we're at positive 1254. Two more that are near my asymptote of negative 3.
Negative 2.99.
Negative 2.99. Good. And one more.
Negative
3.001. Let's start with all that. Okay. Just before the asymptote of 1, I'm way down. So way down there. Just after the asymptote, way up. What else? Just to the right of negative 3, I'm way down. So to the right of negative 3, way down. To the left of negative 3, way up. Okay, so I got those points. Let's focus on the middle. Let's do this first. What would be some good values to check?
Negative 1.
Yep. Negative 1 would be a good one. So we're at negative 1, negative 0.25. Got it? What would be another good one? 0, I heard. 0, 1.3. Another good one? Yeah, negative 2. I think we've got enough in the middle. Negative 2.7. So negative 2, negative 2.7. All right, so what's happening in the middle? I'm going to stay close. Get closer and closer. And get closer again. Okay, so there's the middle. Now let's focus on the left part. I heard someone say negative 4 a while back. That'd be a good one. Negative 4, negative 4. 2, 3, 4. And for me, that's all I need. I can see what's happening on the left. It's just going to stay right next to this for as long as it can. And then it's going to start to curve and stay next to that. Okay, so that's the left section. And now the right section looks like it's going to be kind of like trapped in that little V shape. So what would be another good X value?
2.
Yeah, 2 would be good. 2, 8. So 2, 8, I think is right there. And honestly, that's really enough. So it's going to stay right next to it. Come down. And keep going. Now, if you set a standard window, you're only going to see a really, really small part of that top piece. So let's graph it. But let's set the Ymax up higher. And hopefully the 3 pieces look something like that. So there's the piece in the middle. And again, you're not seeing the whole thing, but that's basically what it looks like. Any questions on that? And I can't draw the verticals, but I could put in 2x plus 3, and you would see that that is the asymptote in this case. That's what the ends are getting closer and closer to. It looks like it actually touches it, but remember, it never actually does. So that particular asymptote is called a slant. Okay, that's a slant asymptote. And the picture that we just did, that's a pretty classic example of a slant with 2 verticals. They usually look something like that. Now you can also have a slant with 1 vertical. That's more common. And when you end up with a slant with 1 vertical, it usually looks like this. It's a little bit simpler because it doesn't have that 3rd piece, but that's generally what a slant with one vertical looks like. Any questions on that asymptote? All right. I think we're gonna skip over this one, but if you were to do it, what kind of asymptote would it be? Would you be looking at a parabolic and behavior asymptote or a slant? Yeah, it would be linear and it would be a slant because the difference here is only a degree 1, and you could use synthetic division to find it. And how many vertical asymptotes would you have in this one? Just one. So this example right here is probably going to look something, bless you, like this. That's basically what that next one would look like. Good. Last one. So this is just to use a graphic calculator to sketch them. I just want to sketch it, and I want to make sure I understand what I'm looking at. Especially anything that might be hidden. Okay, so let's keep that in mind. So we've got, in parentheses, 2x to the 4th plus 7x cubed, 7x squared, plus 2x. I'm going to divide that by x cubed minus x plus 50. Okay, I'm going to start with root 6. Just see what it looks like. What kind of asymptote are we expecting in this problem for the end behavior? A slant. Okay, it should definitely be a slant. Which means, oh, I typed something wrong again. Did I not do divide again? No. Yeah, I did it, just didn't press it. Sometimes that happens. Right now. So let's see if we can see the slant. Slant means we should see graph in both directions. I can kind of see the piece at the bottom. You could zoom out a little bit more. If you set your Ymax, I don't know, maybe negative 20, you could see a little bit more. You're not going to see anything else interesting. It's just going to be the same pattern. Those two segments just continue forever. And so does that. So I would say that's a good overall picture. Kind of shows what's happening. You've got your slant. Well, it looks like you got a vertical in there too, which that'd be a little tricky to find because it's a cubic. But hopefully, if it was rational, we could use the rational root theorem. And you've got a slant in here. Now, to me, it almost looks like it's bending away from it. But at some point, it must start to curve back towards it. If I want to see that, I probably have to go a little higher. Like if we set that to 40 and set the x max to like 20, I bet you're going to see that piece in the top take another little bit of a bend as it continues up into the right. I don't know if you can see it. Can you see it right in here? It does start to curve back towards the asymptote. So that's actually even better. That's a good complete sketch. But is there anything there that we might want to check out a little closer to see if there's something hidden going on?
The table to see if there are holes.
So since we have an asymptote here, we don't have to worry about a hole in this one. Yep.
There might be multiple asymptotes there. Those two lines have been
What, the diagonal one? So for the diagonal one, your asymptote is basically like that.
How can it overlap that?
Remember, it's okay if it crosses it near the origin. Right here, you're only out when x equals 7. But the key is when x is 1,000,000, you're just going to get closer and closer. So that's okay. For the vertical, I think there is only one. You put that right in there. But there's something else there we might want to check out a little closer. Yep.
Oh.
Well, that would be a good question. What's happening right there? Well, it looks like it gets flat. To me, it looks perfectly flat on that window. So let's try zooming in and looking at it. That's -3 to 2 on the x. And let's do -1 to 1 on the y. Let's zoom in and see what happens. So we're looking at the part that looks flat. Okay. So when we look at that, we start to see maybe a little bit more detail, but we should probably zoom in even more. So if we zoom in on that, what do you think I could do for like a y min and a y max? I'm already -1 to 1. What's that?
-2 to 0, maybe?
So then that would mean you would be looking down here. Now you probably wouldn't be able to see anything.
0.5.
So 0.5, yeah, I'm gonna go even smaller. I'm gonna go 0.1. But we had the right idea, just zoom in more on the y-axis. And let's look at that section that looked perfectly flat.
Oh, shoot. It's a really small quadrant. No,
So is it flat?
No.
No. In fact, I think we can tell, you might have to zoom in more, but I can see it from standing here. It crosses 1, 2, 3, 4 times. So in a graph like this, if I ask you how many times it crosses the x-axis, you can't do anything from this big window. That's a good overall picture, but it doesn't show the detail that this one does. Okay? We lose the big picture when we zoom in like that, but sometimes you really need to look at the big picture and zoomed in picture. And that's what I wanted to show you. Something that looks flat, it really is. All right, any questions on that? Okay. So that's the problems for tonight, page 235. It's the same PDF as the homework from last week. Okay, we'll go over that tomorrow, and we'll finish what we're going to do for the week with 4.3. And 4.3, we're done with sketching. Okay, 4.3 is it's all out, so no more sketching.
Thank goodness.